will be very impressionistic. And the idea is that today I will discuss mostly some background and then introduce a little bit of concepts, let's say around two-dimensional QFT, and then tomorrow we'll discuss Wess-Zumino-Witten models. Today it will be more very informal. Okay. So, as you know, quantum field theory is physics, right? And it's about quantum mechanics. Quantum mechanics is about here, but is there actually one there? It's about quantum mechanics. Quantum mechanics is about Hilbert spaces and operators. So you have a Hilbert space, you have vectors called denoted by psi in the product, denoted by denoted by brackets, and then there's a special vector called vacuum, and then you have operators. We call them by V all the time, and they have some label which refers to maybe spin or whatever. There's a label, and then they depend on space-time, which is so space-time here. There's time. We are in Minkowski space, and there is a special coordinate called time, and the rest is called space. And there is a Minkowski norm here. And in that business, one is interested in once people wanted to sort of axiomatize what was doing in physics, it turned out to be that there is a nice sort of axiomatization of this stuff in terms of basically taking these field operators, multiply them at different points, and then taking expectation valuing this in the product. So apply to this privileged vector and taking the product in that, and that's called the Whiteman function. It's function of space-time points. Okay, and then from physical principles and existing heuristic quantum field theories, then one deduced that these things, first of all, should have some symmetry properties under the symmetries of the space-time. In this case, it's called the Poincaré group. So think about translations and rotations, etc. Then in their dependence in the points, there should be also some, one expected there to be some regularity. Basically, these are supposed to be distributions. And then there is an important property of locality, namely these operators are supposed to commute when there is no way to communicate between the two space-time points, namely when the Minkowski distance is space-like, positive. Okay, and that was the sort of setup. And then if you do that setup, first of all, the symmetries tell you how these operators behave under the symmetry generator. So if you look at what is their time dependence, that particular generator is called Hamiltonian. There is an operator and there is a unitary group approach corresponding to that operator, and the space-time dependence is the temporal dependence is just given by such a formula. So this is a consequence of the symmetry axioms. And then the physical properties that this particular operator will be bounded from below. It's called the energy of the theory. And the vacuum, let's normalize it so that the lowest energy is 0, then the lowest energy goes to this vacuum here. And then using the symmetry, this symmetry, you can then write these functions, the temporal dependence explicitly by putting these operators in between every place. And from that you then deduce that this thing, because h is positive, not negative, this should be analytic in the upper half plane of the differences. Okay? So it should have analytic continuation. So from the regularity and symmetry axioms, it follows that these are boundary values of analytic functions, and so you can sort of do analytic continuation in the time variable. So axioms motivated by physics, stated in a natural form, then give you this analytic continuation. And then you can continue it all the way to imaginary time, so replace time by IT, and look what is the result after the analytic continuation. So let me take the functions we had and do the analytic continuation to I times something real, and then call them now the functions of these new variables by a different name. Let's call them N. W is for Weitman and S is for Schwinger. And now the Minkowski property of the Minkowski distance being positive, given what it was, translates in these new variables that the y is actually a Euclidean metric. So y is a Euclidean norm in the y variables. And the commutativity in the space-time, spatially separated points translates into commutativity of these operators, because everybody is now spatially separated. So that's what you read in short version of that you read probably in every quantum field theory book nowadays. So that gave rise to, this is called now Euclidean quantum field theory, because we are talking about not Minkowski space but Euclidean space, and you are talking about commuting operators, and then it's a short step to realize that actually this should there should be some sort of probability behind the whole story. So these operators are commuting, and you interpret them in terms of random fields. So you think about them as random fields, and you talk about, interpret this in terms of correlation functions. This goes back to almost to Schwinger in the end of the 50s, but eventually it was Szymanczyk, physicist, mathematical physicist, who realized that such a setup should be fruitful here. It's not automatic, of course, here. So then you abstract from this that what these guys should be if they come from probability. So you should have some probability space now, not a Hilbert space, but probability space. Expectation, not an inner product. Random fields, not operators. We call these still operators. In physics, it's always called operators. You talk about operators, even if they are random fields, okay? And they are random fields, so they depend on the point in the space, and then you are interested in their correlation functions, denoted by now a bracket. Okay? That's the expected value in the probability. So let's use this physics notation for the expected value. And then you get some functions of, again, these guys, okay? I think I'm sort of now having x's and y's here, so I should really have y's on this side also, okay? Okay, so then you translate. First of all, you can translate what the Weitman axioms become in that language, even if you don't talk about probability. So again, there are distributions, there are symmetries, there are regularities, and it was Osterwalder and Schrader who came up then with a nice set of axioms whose purpose was to answer the question, what sort of axiom should random fields satisfy so that they come from some quantum field theory in the Minkowski. So that's usually called reconstruction. So what if I have random fields and such objects here, what are the properties of them so that you could do that analytic continuation backwards and reconstruct quantum field theory. So to reconstruct Hilbert space, operators, etc. Okay? And they gave these axioms, basically again distributions and symmetries, and one very important axiom called reflection positivity, which we probably don't have any time to go into 60 minutes, but there is one extra assumption. And the regularity also has a probabilistic assumption, which deals with generating function, moment bounds for the fields, but let's not go into that either. So if you're interested in this story, there's a very concise discussion of this in the book by Glim and Jaffe, for instance, from the 70s. Okay, any questions about that?
Small question. You reconstruct the space-time perspective now, from going Sn to Wn. You introduce the time component again, right?
Right, so that comes from the reflection positivity.
Ah, okay. So because you can also have the Hilbert space picture in the Euclidean setting.
Well, I mean, the story here is that how do you reconstruct the Hilbert space, the Hamiltonian? Let's talk about those two things. So there is just starting from the axioms, Hausdorff axioms. You look at time. You look at this particular coordinate, namely time, and there is positivity refers to reflection in the time, and from that there is a beautiful construction of the Hilbert space and the Hamiltonian. But let's not go more into that. We can discuss it later. Okay, so that's the axiomatic story. Of course, in physics, quantum field theory was not done axiomatically. Axioms were extracted from what physicists have been doing, and in the beginning it was done in Minkowski space and operators, and all kinds of Nobel Prize for quantum electrodynamics was mostly people who were working on with operators and doing calculations with them. But there was one person who formulated this story in terms of something which is called path integral. It was Feynman. And all of this, whether you do path integral or not, the physics was always motivated from the fact that you have some sort of classical story, like electromagnetic field interacting with charges or charged matter. And there's a classical story which was in electromagnetic field. It was a story about fields, the electric field and magnetic field, and Maxwell's equations were Lagrange equations in the field theory sense. And so abstracting from that, you have, in that setup, you have fields which are defined on your, now we are Euclidean here. Well, at the moment, let's be Minkowski actually. Yeah. So fields defined on your space-time, and they take values in some space. That's usually called the target space. We will see some examples later. And the action functional is functional. You have some object which is usually called Lagrangian. So a local function. Local means that it depends on the field only through its values at a particular point, or perhaps its derivatives, a finite number of derivatives. So it's a density which you then integrate over your space-time. And then these operators, which we had here in the previous formulation, they are also local functions of this underlying field. Okay? So the operator at value x just depends on the fields and their derivatives at that point. And we'll see examples. And then the Feynmanian formulation was that, okay, you can actually write a formal path integral, namely you take this classical action functional and you take exponential of it and multiply by I and the Planck constant here. And then I take all these guys, they depend on the underlying fields, and then you just boldly do an integral over all possible field configurations, whatever it means. Okay? And the motivation here, of course, is that when the Planck constant h bar becomes very small with respect to what you are interested in, then in the limit as h bar goes to 0, the stationary points of this integral should contribute, and the stationary points are just solutions of Euler-Lagrange equations in the classical field theory. Okay? Now, once you do that, and the continuation in that setup is very simple. You just put the I everywhere, so dx is dt times all the other parameters. So you pick an extra I, which cancels the I here, and you get again the path integral, but now with e to the minus times Euclidean version of the action, namely where you put the I also here. Here is a canonical example of simplest possible example, which has been a toy model for a long time, maybe the Why-4 theory. So the field takes values just in reals, and you take sort of Lagrangian giving rise to the wave equation here. So spatial derivatives and time derivatives, different signs, and then you put some maybe harmonic term to it, and then you add unharmonic term. Now, once you do the analytic continuation, you have Euclidean action where just this minus becomes plus, so now you have sort of Dirichlet energy type thing in the action function. And then the fields we are interested typically are powers of the phi, or maybe gradient phi, some power of it, or maybe also exponentials of the field. Okay? So that's the path integral. Well, once you have that, then of course mathematicians get excited that maybe we can actually make sense out of such integrals, and that's how started constructive quantum field theory in the end of 60s. So question, can you make sense of this as a probability law? Because that's what it looks like, right? E to the minus some positive functional of your variables, and then if you think about this in finite dimensional analogs, then it should be some sort of you could contemplate doing some sort of probability laws of this giving rise to your probability law, which give rise to this swing of functions, etc. When the field is when the action function is quadratic, then so in our toy model, that's just the usual Dirichlet energy plus the by square term. Then this is called the free field. And it's obvious how to interpret this in probability, namely this is just a Gaussian measure. So exponential of this guy is interpreted as a Gaussian measure. And Gaussian measure is completely determined by its two-point function, its covariance. And in this case, if you look what it should be, it's just the inverse of this guy here, this operator. So it's basically Laplacian plus a constant and inverse. And so that's what you end up in the simplest case. And in the simplest case, you see immediately that you have now this problem of sort of non-regularity. The field is not really a function, maybe, because if it's a two-point function, it behaves like that, then when x and y get together, it blows up in all dimensions, starting from 2. So, and 2 is the smallest dimension we can talk about. That's the behavior here. So that tells you that this indeed this particular example should be distribution valued, and in this case it's easy to see that what the regularity is. You read it just from the singularity here, and you see that this it's not arbitrary band distribution. It's in some negative subtle space depending on the D. And especially when D is 2, it's very mildly similar. But it also tells you that you might have problems of going beyond this Gaussian functional, because you see we wanted to do this conformal, and there is a fourth power there. So you don't know how, it's a priori not clear what it means to talk about the fourth power of a distribution. Okay? Well, of course, in physics this was, of course, discussed much earlier. What you should try to do, well, you should cut it off, regularize it. One would maybe convolve it with some approximate delta function, with epsilon being some short distance scale. And then you regularize it, and then when you do that and start doing calculations, you quickly figure out that it's never going to have a limit as epsilon goes to 0 if you put such a thing up there. You have to modify it, and the modification is usually called adding counter terms. Okay, so modifying it, adding whatever you can put there so that in the end you get the limit. Okay.
Can I ask a question?
Yes.
Can you please repeat what is not defined for pi 4?
The fourth power. Okay, if the field is not a function,
yeah,
distribution, then how do you take a fourth power of distribution? You don't even know how to take the second power of a distribution.
Oh.
Right? Because it's not pointwise defined.
Yes.
And what is lambda here? Just a smooth function or scalar?
Lambda is just a number. Okay, so you think about it here that we understand everything about the thing about this here, yeah. And then you want to add an anharmonic term, and let's even put a small number in front of it and see if we can even understand that. But even if you put a small number, you're immediately out of luck because of this singularity. So, okay, so add counter terms, figure out what you should add there, okay, and then try to prove that once you do all of that, so you take the law of this Gaussian free field, which we had here, and multiply it by that factor, and normalize it to a probability measure, show that there's a limit, okay, and call it P lambda, okay. So this was a problem which was, as I said, tackled in the end of the 60s, and basically many people worked on it, but it was started by Graeme and Jeffrey, who more or less completed it in 2 and 3 dimensions. Namely, there the counter terms are very mild. Let's put it like that. You define this renormalized phi 4 just by adding a phi squared term with a coefficient. And the coefficient is completely explicit. In 2 dimensions, it's proportional to this lambda, and there is an explicit number, okay, times log of the epsilon parameter. In 3 dimensions, it's slightly more complicated. There is instead of a log, there is a 1 over epsilon times lambda, and an explicit number, and then there is a log, which is multiplied by second power of lambda. So that's slightly more puzzling, right? It's not completely obvious. And once you do that, then indeed the convergence of these measures was discussed. And that's again discussed in the book by Graeme and Jeffrey very nicely.
So what is the first term in the second line? Lambda. What is the first term in the second line?
Lambda times explicit constant times 1 over epsilon. That's lambda squared. Okay, other questions? In physics, of course, the people were not interested in 2 or 3 dimension because world is 3 plus 1, so 4-dimensional. And all the similarities are much, much worse there. So in our toy case, which is very much like what people were doing in physics, namely QED, you have to, if you start doing that, you quickly learn that you have to add infinitely many of such counter terms. Then everything becomes completely formal. So, for instance, in our toy case, you have to renormalize not only the phi squared, and you also have to renormalize the grad phi squared, you have to renormalize even the phi 4 term. You have some underlying lambda, which is your parameter, and everything is a formal power series of that lambda with coefficients depending on your epsilon here. And turns out that all these coefficients blow up, but they blow up in a way that once you plug it into here and formally expand everything in terms of this little lambda here, then the coefficients have limits. This was a formidable theorem to prove, actually, in the beginning of 50. That's what these guys got their Nobel Prize for. But in the end, it just tells you that there is this formal power series in lambda, which is gotten by doing this sort of magic hocus pocus. Okay. And most of the physics textbooks, if you read them, then discuss in detail how to do that. It goes by doing so-called Feynman diagrams that they enter into these coefficients here. And that's not something which one can do in 60 minutes. Okay? But on the other hand, if you want to learn quantum field theory, you should do some of these physics calculations, because that's the only way to appreciate what actually is going on. It's not enough to read Glim-Jaffe proof, because all of that is motivated by all of this. So. Good? Any questions about that? I mean, yes?
I missed the part where, so this is not for the purpose, or is it missing something?
It's what?
Like the last time you wrote with this series in the end.
This series?
Yes. What was the problematic part with it?
What is that?
Well, there are some problems with it, you mentioned.
Well, okay, so you just assume everything is C infinity in lambda and do the Taylor series in lambda by putting all these things in there. And you try to figure out whether you can choose the coefficients so that once you do the Taylor series in lambda of the whole thing here, then there are some coefficients. And you want to ask question, can I choose these functions here so that these coefficients, Taylor coefficients, have limits as epsilon goes to 0. All of this, there's an algorithm to compute for any given n this Taylor coefficient. It's a sum of so-called Feynman diagrams, and there is a recipe how to make these Feynman diagrams which diverge, these integrals, recipe to make them converge, to extract finite values, and that can be done. Okay, that's a hard combinatorical problem, turns out, and that was solved at that time. But it doesn't, of course, tell you anything about the existence of measures or anything like that.
And so this series is not going to converge.
It's never going to converge. Well,
so you can look at the
there are some cases where in the end it converges, but for some fermionic theories, but in general it doesn't converge. That's where, and that was also immediately observed by the physicists that it doesn't converge, and then you figure out whether you can resum it and all kinds of things you can do, and was done. Okay, so that was one story. That was the story of quantum field theory giving rise to Euclidean quantum field theory, probability, and all of that. But there was there was another story going on at the same time, starting in the, more or less the same time, starting in the 40s and 50s, dealing with critical phenomena. So here in quantum field theory, we were interested in short distance singularities. So when epsilon goes to 0, you take this cutoff away, then think about that epsilon was the spatial cutoff. So take that to 0, then you had singularities at coinciding points. Like here. Okay? It's usually called ultraviolet singularity because short distance means in Fourier space big Fourier numbers, so ultraviolet light. Okay? And but in phase transitions you have infrared. This is maybe epsilon is fixed. You have some crystal, and there are some variables, so-called spin variables. But anyway, locally interacting. So the atoms, variables attached to the atoms, are locally interacting with each other. There's again locality, but the epsilon is fixed. But you are interested in what these variables we saw already in this morning. One toy model for that, the Ising model. But you are interested in long distance behavior. And there was a similar formulation of the story. Namely, again, you take these are so-called Gibbs measures. So you have this local interaction of the spins, except that now it's not in the continuum, but it's on the lattice. And you have some local energy function, depends on the spins mostly around the point x. You weight the exponential of minus beta as a parameter, and then you define expected value of some observables by summing over all possible spin configurations and normalizing it to a probability. And the beta now has an interpretation of inverse temperature. So the h bar, which was 1 over h bar becomes temperature. Okay? So this is Gibbs statistical mechanics. You have, and you want to now look, for instance, how are these guys, what sort of correlations exist? These are now random variables, your field. And now it's interesting what happens in the large distances. So again, so let's look at the 2-point correlation function. Let's look at it not in small but in large distance. And people found out by basically solving the 2-dimensional Ising model that typically these things are weakly correlated when distances are large. So if the interactions are local, then no surprise. Sort of, the first guess would be that, okay, maybe they are weakly correlated when you look at things far away. But then it came as sort of still a surprise that sometimes they are not. And then the thing was called critical. And it turned out that all of that depends on the parameter beta here. So for generic beta, they are correlated weakly, exponentially, but for a particular beta, namely at the critical temperature, there is a power law correlation. So now you have similar divergence here, like here we have in the ultraviolet, here we have in the infrared, in the long distances. And in both cases, we have, if this was really the behavior, not the wiggle here, but not the wiggle, but exactly, then you would have scaling variance, right? And if I multiply the distances by some parameter, then up to just power of that scaling factor, things are reproduced. So here, scaling variance in the ultraviolet, here in the infrared. And this called, of course, for understanding and kind of ideas which led to understanding in physics these scaling variances and also to understand that both of these problems are related was called renormalization group, and is called renormalization group. And the idea is again very simple from the, if you're a probabilist, then you could appreciate it, at least the idea. Maybe you have this field. Let's say that we have all the scales there. So let me call L the scale. So for instance, the free field which we discussed before. You can resolve it into scales. So, for instance, take a Fourier transform and look at the variables where the momentum, the Fourier parameter, is in absolute values smaller than L inverse. So L is a length scale. 1 over L is Fourier parameter scale, and momentum, as it's called. So resolve your field. You can and ask, okay, resolve it into scales and ask what is the law of the field, the filter, let's say the filter field at scale L. What is its law? Write its law in terms of such a Gibson factor. And so let's suppose you can, it's given by e to the minus some functional of the field, and then some a priori measure here. You see, if this scale here is fixed L, then it means that we are sort of like in the lattice formulation we had before. You should think that as long as L is not 0, it's like having a system on a lattice of spacing L. Okay? And then ask, how does this law change when you change the scale? That is called the renormalization law.
In the action that you had above, in the lattice case, did you have to add counter terms already or not?
No, in the phase transition picture, we are not adding counter terms. That's a good question, yeah. So in our case, to solve the problem whether you can construct such a thing, you have to modify things. Here we start with, we understand the microscopic physics, okay, the microscopic magnetic moments interacting, well-defined Hamiltonian, everything fine. You are not supposed to touch it. You have measured it. It's there, and then you want to ask just what happens to these random variables, how they are correlated in large scales.
So you just discretize your action.
Yeah. Well, you don't even discretize, because if you have a crystal lattice, then there is a shortest distance. So the physics has a cutoff. In the quantum field theory, the physics presumably doesn't have a cutoff. You want to understand arbitrary small distances. Okay. So the renormalization group is just that. Okay. And so how does this law change with scale when you change this filtering? Well, suppose it didn't change, it was always the same. Then this would correspond to just having these equalities there. So that would be actually a scale invariant, correspond to a scale invariant theory. And if we're talking about this quantum field theory, then it would say that all these correlation functions, when you scale the distances, they will just reproduce up to some power of the scale invariant. The scale invariant quantum field theory would have this kind of property. One would call this fields scaling fields, and the correlation functions have a scale invariance. And now the story here is that sort of quantum field theories seem to have such scale invariance in the short distances, and the critical phenomena seem to have them in large distances. So this is not true in general, but it's approximately true in one case in short distances, in one case in long distances. And if you have this fixed point, then it's always true. such a fixed point, such a quantum field theory where this is always true is called conformal quantum field theory. And the belief actually is that once you have the scale invariance, you actually have even more than the conformal invariance. We come back to that in a moment. So that's sort of the picture which emerged from this renormalization group picture. Namely, in general, you don't have scale invariance. Your action at scale L that flows. So maybe if you are in very small scales, it's close to one fixed point. And if it's very large scale, you are again close to another fixed point. But in general, it depends on the scale. Okay? So there's this philosophy now. The quantum field theories are, in general, not conformally invariant, but the conformally invariant, conformal quantum field theories are some sort of, I don't know what to call them, signposts or something which sort of govern either their short distance or their long distance behavior. And in general, the physics depends on scale, and it's described by the flow of this renormalization group between the two fixed points. Okay? That would be now you took the 60-minute course, it took you maybe 2 semesters at least, and then you took the critical phenomena course where again you started to do perturbation theory in this long distance behavior and do calculations, and in the end, after all that, you have done so many calculations and you're willing to believe this picture even if you don't still understand it anymore. But that's how the story slowly, this sort of picture emerged. And of course it's pretty far from being established.
Is the passage from scale invariance to conformal invariance comparable to the passage from global gauge invariance to local gauge invariance?
No, I wouldn't say so. Yeah, because when you go to local gauge, again, okay, at least there, you don't expect local gauge invariant theories to be some sort of universal things which talk about other theories, right? I mean, here, this is a complete this is a claim that the space of all quantum field theories is populated by these conformal field theories and their stable and unstable manifolds, and that's it. And everything is there, okay? That's the picture. Whereas those are special theories, like four-dimensional Young-Mills theory is conformally invariant in the ultraviolet, it's just a free field. In the infrared, it's actually not conformally invariant, unless you do something, but in general, it's not conformally invariant. It's this exponential decay business, so most fixed points are. Okay? So now we got to conformal field theory. We are still 15 minutes above quantum field theory.
What is this? What is the statement of the example again?
Sorry?
What is the statement in the example? You're saying that two theories are...
Here I have, sorry, yeah, okay. I skipped this, yeah. So, here's an example. We talked about the phi-4 model in 2 and 3 dimension. And I told you that Graeme and Jaffe told you how to take the limit and define it. And in that case, indeed, the fixed point, there is a fixed point, namely the free field. That's in 2 dimensions, that's a conformal field theory. In 3 dimensions, it's actually not a conformal field. It's one of the examples to this rule. One of the cases where the rule doesn't hold. Anyway, it's scale invariant, but not conformally invariant in 3 dimensions. But anyway, it's a free field, But it's believed that in 2 and 3 dimensions, this theory has been constructed very softly, also in 3 dimensions. It's believed that once you choose your parameters critical, the critical point, then in the long distance, it's actually behaves like a conformal field theory. It's conformal and corresponds, has the same behavior as the Ising model, both 2-dimensional and 3-dimensional. Ising model, which was discussed in the morning, has a critical value of the beta parameter, where it need to be conformally invariant in the long distances. And then this 5-4 theory is believed to have exactly the same behavior. This phenomenon of what's called universality, that many different looking things can be covered by the same fixed point.
So in 4D, the infrared fixed point is briefing. In 4D?
4D, which is not conformal. But in Young-Mills, of course, the infrared fixed point is the vector thing, and that is conformal. And
544, the infrared should be.
544, there is no other ultraviolet stable fixed point except the prefix. That was proven by Eisenman. Some version of that was proven by Eisenman. Okay, so that's the very general story. Now let's go a little bit more detail. Now we are only going to talk about 2 dimensions from now on. Okay? And I told you something about conformal invariance. So again, the conformal invariance you can formulate in every dimension, but let's just talk about 2 dimensions where it's familiar to almost everybody, hopefully. Namely, they are just the Möbius transformations on the plane. So if we have a 2-dimensional plane, we can do the fractional linear transformations. And of course, linear maps are examples. So translations, rotations, scalings. And the conformal field theory in 2 dimension postulates are the following. So you have the Möbius maps, and you have these fields, and we call these fields primary if they have the following transformation law under conformal maps. Namely, if you move the points by Möbius transformation, nothing much happens except that you get the derivative of the field at the points. So the local absolute value of the derivative of the points. So that's the local scaling you have at the point where you're doing things, where your correlation function is, to some power. And that power we call the scaling exponent of the conformal dimension. So that's first axiom. That axiom already has some consequences. Is it easy to see? You can do it as an exercise. 1-point functions can be only 0, either 0 or infinite. And there are examples of both. 2-point functions, if they are not infinite, they are 0 unless the scaling exponents are the same. And if they are the same, they are given by just distance to power 4 times the scaling exponent, times some number which depends on the particular alphas. So just apply this rule as homework. And 3-point function, now you have 3 complex parameters at your disposal when you do these transformations. These are 2-by-2 matrices, complex ones which determinant 1, so 3 parameters, and And you can sort of fix 3 points by doing that. So you just find such a map which maps them to your favorite points. And then you see that the 3-point function will work. The spatial dependence is completely determined by the scaling exponents. And there is one constant which is undefined, which is not unspecified. Okay? That constant is called the structure constant. Okay? Of the conformal field. So 3-point function, spatial dependence completely fixed. There's one number which has to be figured out some other way. 4-point function, now you have more points than you have parameters on the upside, so now there is a full function. So there is some spatial dependence which you can take for free, but then there is a function of, for instance, take the function of the cross ratio of these points, which is unspecified by the symmetry. Okay? So those were the two first axioms. But there is one axiom which is much more hazy. It's called the operator product expansion. This has a long history in quantum field theory. Again, it was in physics when they were studying this in the 50s. They realized that when you look at these fields or operators, whatever you call them, and you take them close to each other, the points where they are sitting, then at least when inserted into these correlation functions or the white functions, it seems that you can sort of replace the product of two fields when x and y get together by some sort of expansion in other fields. Okay, with coefficients which are sort of, so this is now one of these primary fields, this is another one, and here's a third one, there's some sort of sum, and since this has certain scaling properties, then the coefficients are also have certain scaling properties, they are homogeneous functions, the distance of degree determined by those, by the homogeneities of these guys. And if you have a CFT where this holds everywhere, then actually these fields here are explicitly given in terms of primary fields. So that was sort of something which slowly was understood that something like that should be true. And of course, once you understand that something should be like true, then you should axiomatize and demand it to be true, right? So take two primary fields, then their product should be expressible in terms of the sum of the third one. And actually, in this case, one even believes that in many cases that there is a sum, this is an infinite sum, but it's a convergent sum. The structure constants enter there, and then some differential operators acting on these fields here and there, and these are completely explicit, these differential operators. So that's a very strong sounding assumption. So you take your correlation function, you take two such fields there. If you take, so the guys which have the closest points, pair of points together, then you can replace them in the correlation function by such a sum, where the structure constants enter and some differential operator acting on the rest. Okay? And this differential operator is even determined by conformal symmetry. If that were literally true, as I said it, it would mean that the endpoint function could be iteratively determined in terms of just the structure constants, because they come here. Every time I can get rid of one of the fields one at a time, and I get always a structure constant, I get some differential operator acting on the rest. But once I've done it so that I have only 3 points left, then I have this explicit function of disease. So all the differential operators just act on this simple function here. So everything should be completely explicit. Okay? So that's the motivation. These axioms, sort of, if they hold in sufficiently strong sense, they tell you that the correlation functions are completely determined by if you know the structure constants and if you know what the primary fields are. Question?
If you say that the operator character expansion should be convergent, in what sense do we need it to be convergent?
That's the devil in the details. For instance, in Ising model, it should be convergent. In Liouville theory, it actually turns out to be convergent, even if it's not a sum, but it's even an integral. But again, how do you make sort of axioms which capture all these cases? This has been studied. There are some recent attempts to rethink these things again, because people have been doing this in other organizations. But of course, there are two things. What are the good axioms, and then whether your examples actually satisfy the axiom. Okay, but let's not go more to that. Okay, there was a. I'm not going to talk about. There's no way in the 60 minutes we're going to talk about that. And, so I rather just stop here about the conformal field theories. But this is the thing which you want really to understand if you have a conformal field theory. You want really to realize this sort of picture here, that it's in very strong sense explicitly solvable in some sense. But the catch is that you have to figure out what are the primary fields and what are the structure constants. And how do you do that? That's another story. Okay? But even there is another. We can also go back. So how do you? I told you that there are these conformal field theories, but we haven't seen a single example. Okay? And actually, people haven't seen many examples. Really, very few examples, explicit examples, even on a heuristic level, you know. So I said one way is to try to guess what are the primary fields, what are their dimensions, and then there is this sort of consistency condition when you do this operator product expansion. It's called conformal bootstrap, or crossing symmetry, and this was very successful in physics. So it was very successful in 2 dimensions. And later also in higher dimensions. But then, okay, you can sort of get guesses what might be true. Another one is that you just try to construct it from the path integral. Okay, at least we saw some examples of path integrals, and you would like to construct it out of path integral. So you construct quantum field theory, all the correlation functions, and then you try to do it for a case which you believe to be conformally invariant. Okay? And again, question what would be the examples. And in 2 dimensions, actually, there are plenty of examples to work with. And I'm not sure when do we have it.
I think now is the planned time.
Yeah, you're the boss. You're not standing like Evelina was standing.
I think it's a good time for a break.
I think it's a good plan, yeah. The rest of today, I just want to discuss some examples, what we would like to do, and then tomorrow we discuss a particular example.